look at the next group of questions from the Regents exam, 16 through 20. Question 16 is again in the similarity right triangle area in the B cluster, which as I look at the question, it deals with dilations and scale factors. Certainly it can be classified in there, but I think the A cluster is probably where you learn most of that information to make it easy. So I'm not exactly sure why it's B, but definitely there's some A and B, I guess, in it. In question 17, the cluster is COC, which is the congruent cluster subset of proof of a number of things, speaking specifically to angles. And the angle ones are obviously our transversal parallel line relationships, and we're looking at alternate interiors, things like that. In this one, we are back in similarity right triangles, cluster A, which is again a dilation kind of a question, the basics of how to dilate, how to determine scale factors, a fairly straightforward kind of a question out of dilations. And then here we have another modeling question. This one is mostly about area, and then it applies a model to it. This is the classic painting problem, calculate some surface and area, and then determine how many cans of paint. Classic problem. And then this one here, you've got C, which is circles, and this is the relationship of equal angles based off of circles. So you're mixing things like an inscribed angle, a central angle, a tangent secant angle, those types of things. It's a good little problem and need to know a lot of properties from circles. So let's take a look at them individually now, and also at the materials that would have helped your students succeed with them.
Question 16. If a triangle ABC is dilated by a scale factor of 3, which statement's true? Now this is classified in the B range. I really think it should have been A. This is about dilation and dilation properties, and so I think this should have been an A cluster. That's okay. I'm sure they had reason to have it in B. I guess this is classic, and again, the materials cover this so nicely. These two problems or answers are just bad because they're trying to trick the student into thinking that angles grow proportionally. But we know angles are congruent in a dilation. This one, of course, is testing to know if they understand when something gets 3 times bigger, how do you create an equation to balance that? And of course, the bigger item doesn't get multiplied by 3 because it would never equal the smaller item. So this is our answer. 3 times the original segment length will match the image if we go 3 times bigger. So classic kind of a question. We'll look at a couple examples in the notes and worksheets that'll show you that we'll hit this thing hard. Alright, to look at a couple of the items in the notes and worksheets and things, just to quickly give you a feel for it. We definitely get into that whole idea of what a dilation is doing. We look at scale factors. We define it very clearly what the scale factor does, how we do the image over the pre-image as a way to describe scale factors. We get into this idea of angle measurements, and angles will always stay the same while the sides become proportional. We see that kind of relationship going on. We will spend time in one of the worksheets actually developing, physically measuring those angles to establish that the angles didn't change and that that's part of the parallelism that's formed. We will look at problems where we'll give you the relationships and you got to find the scale factors, or for instance, like in these ones, these are a lot like the actual question where we say a dilation is taking place, and is this angle twice the size of that angle? And that's basically the exact question in a little bit different format. But we have to think, wait a minute, angles are equal, so this is a false statement, and so on. Lots of things to establish that idea. Question 17 says Steve drew a line segment, and he's got it here, lots of information, a scalene is formed, and so on. And then they ask us which statement is true if we know these lines, that would prove them to be parallel. So this is the converse idea, is we want to establish parallel lines. So we're looking for the ones of alternate interiors being equal, corresponding angles, and so on. And so all I did is I moved through the groups, kind of looking where they were and looking for one of the angle relationships formed. And of course, this is the alternate interior pair, and we got it. We'll look at the notes where we establish the ideas of what are the relationships found in a transversal when it cuts two parallel lines. Underpinning concepts here in this question are well set up in our notes. In C9, we definitely get into this business of parallel lines, how corresponding angles are formed through a translation down array. We talk about corresponding and alternate interior, and all of those things are set up. We then look at lots of types of problems that deal with alternate interiors, explaining why they're equal, getting used to the terminology, the names of the relationships. We get into here some assessment items where we're talking about, relationships between parallel lines and alternate interiors. Here we're asking a very similar kind of question that says, what do you need to know to say they are parallel? So again, the converse idea being established there. Lots of support for this kind of idea. Question 18 talks about a dilation, and the wording is a little tricky. It says CD is the image of AB. They've kind of written it normally as, it might be written a little backwards. Students would assume the first thing's written as the pre-image kind of idea, but it says CD is the image. So CD is a reduction. We know that this is a reduction because CD is smaller than the pre-image AB. And then it kind of goes after scale factors. Now the key to scale factors, and the notes handles this awesome, is that we relate the image always over the pre-image. So in this case it will be like, we would be looking for like CD or DC over AB or BA. Now none of those are available. So the one that works, of course, is CD, the image over the pre-image. So again, we go here to here is our image distance, and then we go to our pre-image distance. So this is our value. This is trickier because of the abstract nature of the notation, and they didn't use the physical segment, they used the dilated point there, which is fine. We cover all of that. We've already had one from the standard recently, so I'm going to show you a little bit different area here about the notes. Here's where we talk about how we dilate lines. And then it gets into the the details about that these have to be parallel. We talk about the angles that are equal in the diagram. Start to talk about the scale factors evolved there. Then, as you've already seen, we have problems that are not quite like this one, where we give the lengths and ask for the scale factor. A question that's a lot like the one we're dealing with is when it's not the physical segment lengths, but the length of the from the center of dilation to the image and to the pre-image, and then talk about the scale factors. And so this is basically many questions that are identical to what we just got asked to do. 19 gets the tag of a modeling problem, which is fine. This is really area, and it's classic area. It's the old paint can problem where you have a certain surface. So really we're calculating area, and then we're seeing how many cans could paint it. We're talking about the outside surfaces of a cube. So there's 6 outside surfaces. They're 12 by 12. There's your surface area. And then we say how many cans cover that amount, and so we divide by the 450 square feet, and we find out just under 2 cans. Now you can't buy a can and a half or whatever, so we would have had to have bought 2 cans. You got to round up. The modeling question gets at, first of all, the idea of area. I just wanted to kind of show you that while area isn't directly kind of one of the standards, it talks about volume and establishing the understanding of volume, so you got to have area, but we certainly went into depth about where the formulas come from and the relationships found there and what it means to be half of a rectangle and lots of things as I wheel through them, trapezoids and different ways to find area of trapezoids. Lots of hands-on kind of counting and sliding and shearing, different techniques for calculating these things, just to kind of really set up the heart of knowing what area is, and then being able to apply it like in a modeling problem about surface area and paint. Question 20 is a great question about circle properties and relationships. It tells us what's perpendicular, that there's a tangent line here. It talks about chords and a diameter. So I want to go through each of these because they're great relationships. This says ABC, so ABC, that's 90 because it's inscribed on a diameter, so I know that's 90. And ACD, ACD is that relationship of a diameter and a tangent line, has to be 90. This will be true every time. Let's look at BAC. BAC, this inscribed angle is half of this arc. But guess what? DCB is also half of that arc. This is a secant tangent angle. This is an inscribed angle on the same arc. This will also always be true. Awesome stuff. Let's see, CBA, the 90, and AEC, also 90 because it's inscribed on the same diameter, so it's also 90. They're always equal. The one that isn't always true, it would be ACB and BCD. Yeah, this arc does not have to equal that arc, and so those angles will be slightly different most of the time, unless, anyways, it's hard to answer for sure. This question is a great question because it does diversify like the product in terms of what you need to know. Let me just quickly zoom through a lot of material to get to where I want to get to. This question deals with the idea of inscribed angles. It deals with being inscribed on a diameter. It deals with, let's see, also tangent secant angles. Let me get to those. Here they come. Secant tangent angles and the relationships found there. There is a lot dealing with this question, and everything is well laid out. You can see I designed diagrams that relate multiple types of angles: secant, tangent angles, inscribed angles, central angles. Students with these materials are very used to very complex diagrams and relationships. Here are more examples and worksheets and assessments of where those kind of angles are very intermixed with each other.